Hi ladies and gentlemen, I wanted to talk today about linearization. This is an extremely important concept and something that is used all the time in science and engineering, and I'm not really sure that ZIL does a very good job of addressing this topic. So we understand the flow of how we're going to analyze nonlinear systems. This is the nonlinear system that I've selected for today in order to provide an example for us. And what I want to do is I want to just start and go through this, but really emphasize this third step here, which is generating the linearized system and explaining what that really means. So of course we're going to start with critical points, and if we solve this, you can see for yourself that the critical points are -1, 1, and 1, 1. Similarly, we can find the Jacobian, taking a few partial derivatives, looking at the rate of change of x and taking those partial derivatives. We have a 2x and a 2y, and then the rate of change of y, taking those partials, we have a 2x and a -1. So this is the Jacobian matrix for the system. And what we're going to do to linearize is we are going to look at what a linear approximation around one of the critical points looks like. And we can do this for every critical point, and in general that's exactly what we do. So the idea over here, that I'll show you some phase planes in just a minute, but I just have a need to communicate to you the simple idea of what we're doing. So we found the critical points at 1, 1 and -1, 1. And what we're going to do is we are going to select two new variables, u and v, where u and v are the variables that give us a transformation of the xy coordinate system onto the critical point. So what we want is, in the xy system, we want x and y to map to u and v, where u and v will be 0, 0, the origin, at the critical point. So to do that, it's pretty straightforward. We just take u and set it equal to x minus the value of x at the critical point, which in this case is -1, so that'll become x plus 1, and then v is equal to y minus the value of the critical point, which is 1. And this transformation doesn't change the dynamics of the system at all. Literally all we're doing is taking a coordinate system and shifting it over to a new location so that it matches up with the critical point and puts the critical point at the origin. So looking at this, we can see that u prime is equal to x prime and v prime is equal to y prime. And it turns out that our linearized system is uv prime. The rate of change of uv is equal to some matrix, because of course it's linear, so if it's linear I can use a matrix, multiplied times the new coordinates to uv. And this isn't necessarily well understood, and I'll explain this at the end of the video if you want to hang on for the explanation as to where this comes from. But this is the Jacobian evaluated at the critical point. So let's come back up here. The Jacobian at -1, 1, that's what we need to put into this matrix location here, and that's going to be equal to -2, 2, -2, -1. And like I said, at the end of this video, if you want to stay on, I'll explain why that is actually the correct thing to be using. So this system is a linear approximation to the nonlinear system up here at the critical point -1, 1. So what I want to do now is dig into that a little bit more, just to explain exactly what it is when we say that. So we have a linearized system which we can analyze, and that's why we've done the linearization. This nonlinear system up here, we can't analyze that. There's nothing we can do with this, because we don't have the tools to be able to solve it or to even be able to analyze it. We can take a look at the phase plane. That's about it. So in order to come up with some more concrete information about this nonlinear system, we evaluate these linearizations around the critical points. So let me just show you how this works and give you some idea of exactly what linearization actually means. The idea is the same thing as what you did in calculus. Let me run this. We're going to start over here. I'm running a program, a script called Linearization. So it shows us the critical points. In this case, -1, 1, and 1, 1. The critical points we're going to evaluate at each one of them. So at -1, 1, the Jacobian is exactly what we found, -2, 2, -2, -1. And the eigenvalues are complex with negative real parts, so it's a spiral sink. And similarly, we have another critical point at 1, 1. This is the Jacobian, and it is a saddle point. We'll look at that later. What I want to do right now is emphasize this graphic we have right over here. So this is actually two phase planes on top of each other. Underneath is a dark gray phase plane, which is from the nonlinear system. On the top is a red phase plane, which is from the linearization. And what this picture shows is that very close. You see we're going from -9.8 to -1.02. And similarly, I have 400ths along the y-axis here. So as long as we're really close to the critical point, the linearized system is an excellent approximation for the nonlinear system. And that's what we're taking advantage of. What I'm going to do now is just run this forward. And when I do that, we're going to see that the MATLAB code is going to pan out. And so it's going to back away from the critical point, and we'll see that the linearized approximation becomes less and less good. So you see as we're moving back, you start to see those dark gray arrows because the red linearized approximation, which is everywhere a spiral sink, actually doesn't match up very well with the nonlinear system that it's trying to approximate when we move away from the critical point. Let me show you a couple of graphics that I think will help to clarify this. So the first one here, this is the actual phase plane for the nonlinear system. And we can see over at -1, 1, we have something that looks like a spiral, and over at 1, 1, we have something that looks like a saddle. Figure number 2 is the linearization of the critical point at -1, 1. So I'm just going to show you these kind of side by side, and we can see the dark gray is exactly the same in both phase planes. So the red is the linearized system. It is everywhere a spiral sink because a linearized system only has one critical point. And in this case, it is a spiral sink. So the entire system is a spiral sink. So as long as we're close, that's what the third picture shows us. So the third picture shows us that as long as we're close, this linearization does a nice job of approximating the nonlinear system. However, the farther we move away, we begin to see these large disparities between the approximation and the real nonlinear system. And that's just highlighted in the second and fourth figures here. The fact that the farther we move away, the worse that approximation becomes. Let me show you this whole thing again with the other critical point. So this was with the spiral sink, and I only have to change one thing in the code here. It will rerun all of the linearization, and it will show us the critical points again. But what we're going to do is we're going to look at the critical point near 1, 1. As we saw previously, if I'm in close, my linear approximation for the saddle point is quite close. And I can see that this is a saddle point. That's fairly straightforward. Now we're going to do the animation where we back away from the critical point. So as we move backward, we see that it becomes a less good approximation. And going back to our figure number 2, we can see near the critical point, the linearization, the red arrows are a good approximation, but the farther we move away, the less good that approximation becomes. This is the whole point of linearization. We want to have good approximations to nonlinear systems, and to do that we have to pick a point that's of interest. And what's important to us for dynamical systems are the critical points. And so that's why we choose to linearize around the critical points. In order to actually evaluate what's happening, we use the fact that the linearization and the nonlinear system behave similarly, And so if we analyze the linear system, the conclusions that we draw, for example, saddle point, apply to the nonlinear system. That's the idea behind linearizing. So that's it for this video. If you want to stay on for a minute, I'll explain where that Jacobian matrix actually comes from. All right, for those of you who are still with me, I've gone back to OneNote, and what I want to do, I'm going to do everything here in the green pen. I want to really dig into this change of variables, because this is what gives us the information about the linearized system. So I'm going to copy it back over here. U is equal to x plus 1, and v is equal to y minus 1. And the way in which we decided what these are going to be is exactly what we said previously. It's x minus the x coordinate of the critical point and y minus the y coordinate for the critical point. Let me rewrite these solving for x. So x is u minus 1 and y, which is going to be equal to v plus 1. And then let me also note the derivatives. X prime is equal to u prime and y prime is equal to v prime. What I'm going to do is substitute all of this information here into the system of differential equations. So if I take this and put it in, I'm going to get x prime, which becomes u prime, is equal to x squared, which is u minus 1 quantity squared, plus y squared, which is v plus 1 quantity squared, minus 2. And the other equation becomes v prime equals u minus 1 quantity squared minus v plus 1. So all I've done is transform the system from x's and y's to u's and v's. Continuing, u prime is equal to u squared minus 2u plus 1 plus v squared plus 2v plus 1 minus 2. Similarly, v prime is equal to u squared minus 2u plus 1 minus v minus 1. You'll notice that the constants here cancel out. And what we're left with is u prime is equal to minus 2u plus 2v plus u squared plus v squared. Scroll up here. Similarly, v prime is equal to minus 2u minus v plus u squared. This is the actual system that's been transformed from the xy coordinates to the uv coordinates. And that, again, is just a simple translation. We've just moved the axis system. Now we want to linearize about the the critical point for the uv system. So we built this system specifically so the critical point would be at the origin. So the critical point in the uv notation is 0, 0. And we want to linearize about that point, 0, 0. Well, to do that, what we're going to do is we're going to realize that for values near 0, everything that has a power greater than 1 is much less than the linear term. So, for example, if u is equal to 0.01, u squared is equal to 0.0001. So when I'm close to 0, the values of the higher order terms actually are considerably smaller, and I'm going to approximate them to be 0. This is the idea of linearizing near the origin. So in this case, u has 100 times more influence than u squared. What that means is when I approximate u prime and v prime, what I'm going to do is I'm going to assume that these higher order terms are equal to 0. And what that leaves me with is u prime is approximately minus 2u plus 2v, and v prime is approximately minus 2u minus v. This is the linear approximation in u and v. But wait a minute, that is exactly what this is. They are identical. this is equal to u prime equals negative 2u plus 2v, and v prime is equal to minus 2u minus v. There should be a negative here because I typoed that. My bad. This should have a negative 1. When I did the Jacobian, I messed that up. All right, so what we see is this is the process of linearization. What we've done is we've switched over to make the origin equal to the critical point, and we've done that by changing from xy to uv, and then linearized around that origin in the new coordinate system, uv, and what we end up with is exactly the Jacobian matrix. This is why the Jacobian matrix is the correct thing to use. All right, thank you very much, and good luck with the homework.